Howdy out there. I'm trying to talk about carbide insert tooling, and mostly on the lathe, but it applies to anything. But actually, on the lathe is probably the easiest way to. Now, I have a Sandvik e-learning course here. This seems to be a pretty decent course. Of course, if we're in the Titan building blocks and you're in the Titan rocket section, get our Kennametal tools. I actually tried to find some e-learning in the Kennametal tool side, but there's a lot of good stuff in here. You get the Rocket Tool Library, and actually we use Kennametal in our school, so we use a lot of the Kennametal tools as much as we can. But I'm trying to find a good, easy to learn basics course, and the tooling companies tend to get very deep in the subject, so I'm going to use some of their stuff in order to give a more introductory lesson in here. So I was actually poking through this introduction, and I went to the theory section. It actually had my data from a couple of years ago. So anyway, we have a lathe here with a carbide insert tool. Turns in this direction, so it's the chisel effect of the insert based on even hand ground high-speed tool that I had to grind in my first machine shop class, and I have other people in our class do the same thing. We grind our own tool, and the first manual lathe cut we make with that.
This is the fundamental operations for turning.
I hope that wasn't too loud. I meant to turn that down, but anyway, we got facing and turning. We'll just let that play again. Turning and facing. Generally, I do facing first and then turning, and I believe Tyson does the same thing. But we need to figure out RPM and feed rate. And on the lathe can run in RPM or constant surface speed, CSS, also known as surface feed per minute. Whether you're in the Americas, it's going to be surface feet per minute or some other calculation. It's like if you laid out a roll of a round object and laid it flat. How many feet per revolution? You just do a calculation for.
Let's look at the definitions of spindle speed.
All right, you got spindle speed, which is RPM, and cutting speed, which is expressed as that surface speed, or they have millimeters per minute or feet per. Oh, no, I'm sorry, meters per minute and feet per minute. So it'd be if you were to unroll the round object and rolled it flat, how many feet would it cover? This is in a round, not linear. That's like the formula to calculate RPM. Because as the diameter changes, you're covering more or less ground per revolution. Which gets into that circumference thing and pi and all that stuff.
On this page, you can learn how to.
All right, so you get definitions of cutting speed. And I'll tell you, they get really crazy on the math formulas. There's actually a simpler one than this, but you got your tool on center line. This is how a lathe tool cuts. As it rotates down, it starts cutting. And as the diameter gets smaller, technically you need to be going more revolutions per minute to keep the constant cutting motion, or how fast the metal goes past the tool. We end up with a chip. And then we got to figure out the depth of the cut and how many. So the first thing you want to know is RPM. So in a lathe can run in either RPM or constant speed CSS. And in the G-code language, in most Fanuc or Haas lathes or Fanuc controlled lathes, you can switch from RPM, which I believe is the G97 mode, or the surface feet per minute mode, which is G96. And you want to do most of your cutting in the G96 mode, except for anything that's on center line, like drills and taps, things like that. And threading tools, I think some people do also run it in straight RPM, and sometimes grooving tools. So let's go to the next one. But this is actually a much easier calculation. It's a little bit like the third step of this one here.
Here you can see the difference of the circumference.
All right, so you got your big tractor trailer tire and your little boat trailer tire. You're both going down I-75 or I-95. In order to keep the feet per minute the same, the little tire's got to go more RPM than the bigger tire, but they travel the same rate. So in order to go 70 miles an hour, the little trailer tire, has to go faster. That's pretty much all you need to know. You got this C equals pi times diameter. A lot of math, though. Okay. So a lathe can run and self-adjust. That's the beauty of lathe versus a mill.
Use the formula to see
All right.
the difference of cutting.
So as you start out here, it actually is going to rotate slower. As you get smaller, it should rotate faster. Now, if you have it in plain RPM or like a manual lathe, you cannot do that. You're going to have to, everything's always a compromise on a manual lathe. But in a CNC lathe, you want to run it in that constant speed mode.
Mouse over to get more information.
And when you're in your CAD/CAM system, there's a selection for that. Make sure that is always active, except on the drills, taps, threading, things like that. All right, so you got RPM. We're going to run in feet per minute or meters per minute. Then you got to figure out how fast you can go in that direction. And a lathe runs in, I know everything here is metric, but we're in the US, so we run in inches per revolution. Now in a mill, you run inches per minute. It's really a calculation that's the kind of like the per revolution thing times how many teeth in RPM to get the inches per minute calculation. But we're just talking lathe here. And it's actually much easier. A lathe only has one cutting tooth, so you don't have to add in any formula. So every revolution, it's going to cut. It doesn't matter how fast or slow it goes, it's going to be hooked to that. And that's how manual lathes run, by the way. You set them up to run, and it's always going to be in thousands, like from 1,000th up to like 10 or 20,000. 20 would be really fast, 20,000 per revolution. So if you were to run at 2,000 per rev, that would be a very light cut. And then it depends on how deep you go. So that's something you got to use on experience. And if you're not sure, like if you know aluminum and you're going to stainless, 304 stainless, as long as you have your surface feet per minute calculated, you pretty much can just go right and start cutting the other material as long as you have the correct insert. But because you 304, you rotate slower, but the inches per revolution should be the same, the cutting rate. And then your depth of cut, you can adjust that by. That's really depending a lot on horsepower and rigidity and stuff like that.
This is the
Okay, you got your calculating data, but on lathe, all you need is to have that basic SFM number. Now, I find a lot of times I can't find like a quickie chart for that, so I actually end up using the carbide end mill chart to just get me in the ballpark of range, because they all have a ton of those on surface feet per minute range for different materials of metal that you cut. A lot of math there. So
See the difference of inclination and
then you get
how it affects
style of inserts. You have inclination angle here, because this is in a negative view, and rake angle. So you get little different orientations. You get your chip formation, and a nice cutting one would be little curly cues that I think some people call them C's or 9s or something, but they cut up and break off. If you get the long stringy chips, that's not optimal, but
play the movie
try to do our best.
and effect
You get feed rate. Now, if you ran a faster feed rate, the spaces between each would be very coarse, and you'd have a rough finish. You'd have a uniform finish, but you know, how you cut that, and also which way the insert points. So this one is actually has less contact area, and this one's got more contact area.
The smaller the entering angle, the more
All right, so you got all this. There's a lot. You get really deep into the subject here, but up here you got different style inserts in their contact area. Like this one up here, I like using these style inserts. This looks like a D&MG right here. This is your real common inserts. And the C series is 80 degree. The D series is 55. This is called the W. And then when you get into this area, this is a square insert. Then you get into triangular inserts. And the V series, which is just a smaller. So your basic tools that I've seen are the C, the D, and the V. Some people like the triangular ones. This one's another square insert, and then you get round ones. Rounds are actually very heavy duty, but they take a lot of horsepower. And inserts, you can rotate them for more cutting edges. Most of them have 2 to 4 cutting edges. A round one, you can just keep on rotating.
use the formula below.
And you get turning theory. So a lot of math there. Let's skip the math. Oh, I completed that end of the course. Okay, let's go back. Let's take me back. No, I guess I got to go back here. Selection procedure. Okay. Did I finish that one? No, I want to do it again. For the benefit of the crowd. We could talk about the rockets right here, so we can, oh, let me sign in. Oh, I'm in. Go. Log in.
This course presents the selection procedure for the
Okay, got the
production
rocket
process
library.
returning.
right here.
Talking about the tools you need to get, so really excellent basic course. Oh, let's get back to this one. Selection procedure.
Selection procedure.
All right, you got
production planning process.
component, what do you need? Machine, choice of tools, how to apply, troubleshooting. All right.
To get more
I think this has actually got some good videos of real up close videos of cutting tools. What did I finish this thing already? Hold on.
This course gives you an
I
understanding.
guess there wasn't much in that section. Okay, choice of inserts. Here's a pretty good one here. Get your cutting tool. Normally they don't face that way. They like to face the inserts so that cutting direction is towards you and the chips go the other way. But this is probably for demonstration purposes. Most lathes don't run in that orientation because you'd have to turn in the opposite direction. You know, it does look like it's going like towards us. All right, let's go to the next one. All right, they tend to use categories for workplace materials, P, M, K, and A such. You can't remember them all the time, so it's a good thing I have some charts. You don't need to really remember them. This is an excellent up-close view of a cutting chip. You can see the insert right here. This width, if you were to measure this insert, I mean, it looks kind of ratty right here, but that's your inches per revolution calculation, which is going to be in thousands, you know, from 2,000s, 5,000, 7,000. So that'll be how much it's digging in per revolution and maintaining that cutting edge. And nice curly Q chip there.
Mouse
Right.
over the material
You got
to learn
6
more.
main categories. You got your basic low carbon steels. That's the chip. You got your stainless steels. If you click on this, it'll tell you about them. Have chromium in them, which keeps things from rusting, but they're a more difficult material to cut than basic steel, which is like your cold rolled or your hot rolled steels. Then you get into cast iron, which tend to be a crumbly chip, and you can cut cast iron with no coolant at all. Then you get your non-ferrous materials. Everybody loves those. Like aluminum is the very most common one, but you have brass and bronze and stuff like that. Then you get into your super duper alloys, which are your that have high nickel, iron, cobalt, titanium based metals. So you got titanium, you have Inconel, waspaloy, all those super duper metals. But like I said, much more difficult to cut with shorter tool life. And then you got your hardened steels. And there's also machining of hardened steels versus tool steels that haven't been hardened yet. Okay, get your basic categories, because if you're looking for inserts for the lathe, you want to make sure you're in the right category, because like you might find an insert that can cut steel and stainless well, but it won't do Inconel. You might find a good aluminum cutting one is not good for stainless. But most of us try to find one that's a good combination. Maybe you have a tool holder and you have two different inserts you use depending on the material.
Let's look at the different ways of chip formation in
So you
the
got
turning
your chip breakers, you want them to break. And this looks like a long curly Q. I'm not much of a chip breaker there, but you notice I used to hear that all the heat should go in the chip. If everything's cutting well, all the heat would be in the chip. And the part should not really be that warm if everything's going perfect. All right. You want to know about insert rake angles. So this is actually, they call this a positive rake, the chisel going up. This is like the best cutting addition because it actually doesn't require as much horsepower as the negative rake. Plus, this gully here is called the chip breaker. So that's built into the insert. Every insert company's got their own little formulas and stuff. And also depends on the metal. So, and the grade of the carbide also makes a difference. So in the early days, negative rake inserts were like the insert to have, but they required more horsepower. And these positive rakes would not hold up. Now, pretty much everybody's got positive rake inserts as far as I know. But sometimes it depends on the recommendation, and your tooling guy is actually a good source for that.
Let's look at the difference between
All right, so you get negative. Now, the positive could be built into the insert, or it could be how the insert's tilted. Or in this case, this is actually negative point of view, and you always want to have clearance on that's what you learn when you first grind a tool. You got to have clearance there. You want this edge here to be the only touching part right there.
By clicking on the circles,
this is an up close view of your insert, and you have the front part's called the tool nose radius, and you have to know that. You can have a similar insert that's exactly the same, but it has the most common ones are the ones with them with a number 1 on the package or number 2. Number 1s are 15 thousandths, so 1/64th, and the number 2s are 1/32nd. That makes a big difference because when you do your curves and your chamfers, they may disappear or they may be overcut, and you won't even know it because it's hard to tell on those ones because you have to know, but if your CAD can't program it, you've got to actually be calling out the correct insert type. Make sure you use the correct insert in your machine.
the ER treatment gives the
All right.
cutting edge the
And what's this? Reinforcement.
Each insert
So we got
has
here
its own
working with
unique
insert.
If
You
your
get your
tool
style of
correctly
chip. So your chip breaking is like optimal. That's what your
chip
goal
breaking can be
is.
classified in 3 main
Sometimes it's like sometimes you need to feed harder, or you got to maybe go deeper or lighter. You know? So you got your roughing ones, maximum stock removal. Sometimes you use a roughing tool and a finishing tool. That's especially in your steels, so that you can keep the finish nice, but the roughing tool can can take more of the abuse. You might even use a different style tool for roughing versus finishing. You got medium and finishing, small depth of cuts and low feed rates, where maximum you just try to remove metal.
Click on the blue fields
Chip breaking,
diagrams for optimized performance.
not sure what that chart is trying to tell me.
The correct insert
Size, they're actually classified by size and thickness. But if I'm looking for inserts, like this is, the P series, which I forget what that was. The K I remember is the cast iron. I'd have to go look at that chart again. But if I'm ordering inserts, I'll use my local tooling supplier, which is the MSC Industrial Supply. That's what we use. Or we have our local dealer, the AFI. I'm going to go sign into my account here, our school account. Go to my pre-built lists here. But I go to hunting around. I got Titan lathe here somewhere. Got a whole bunch of lists here. Titan tools. That should be tools. We have Titan Maybe I combined them. Let me just take. There we go. Titan lathe. They went right by it. We had some other kind of metal tools we decided to keep on using, but we got inserts. We had a different grooving system. We just wanted to make sure we had the right width and wanted to have the right grade. These are grooving inserts. Internal. We wanted to get the correct boring bar. It had a little tiny insert in there. This is another grooving one. Grooving. The grooving tool. And we had this kind of metal R MVJN one, which let's just look at that. We didn't have the top-notch style inserts. It's, if that's the one. We had to order another B series. I'm sure that I thought that was the one. Yeah, this is a D series negative rake holder. So we go to the big book catalog on the Kennametal. All right, there's all the tools up here. You got your different orientations and stuff. So you had the D series here, and it says the insert size, shank size for the machine, or if you have an ST10, but you get shank size and insert type. So you look up with the D series inserts, spare parts. So that's kind of what we came up with a nice little formula there. All right, let's go back to the, where the heck is it? If there's any more stuff to learn here. So you can get pretty deep into this. Dedicated inserts, general insert, we're more general. We like to have just something that can work all the time. Negative, positive rake inserts. Notice you got the little chip breakers up here. Coatings. Coatings are a big thing. All the temperatures should be right up here. It's almost molten metal when it cuts. Or it's deforming. You got ceramic inserts now, or cermet, or diamond coated, but carbide's your standard right here. You got cemented carbide. You can actually kind of learn a little bit more. What's a cermet? Coated with a carbide cobalt binder, polycrystalline, all different types. Is all we go back to that chip breaking stuff. I want to see if we get any more videos on cutting, actual up close videos, different insert shapes. Most of them are basically common shapes. Oh, here's a good one on nose radius. So you got small nose radius, large nose radius. So ideal for small cutting depth, reduces vibration, but it has a weak cutting edge. The depth of cut should be no less than the nose radius. Oh, that should be, that's a pretty interesting term. So if we had a nose radius of 15 thousandths, we should have at least 15 thousandths depth of cut. Okay. Never knew that. A small radius should be the first choice. Get in there. Plus, it's also going to depend on your part. If it has internal radiuses, that's going to also affect it. Increased depth of cut helps to direct cutting forces. Nope. We want to see some videos. You got your wiper stuff. Wiper, surface finish. Hold on a second. I went back just to check it because now you got specifics on parting and grooving. Okay. One on threading. Then you get to milling, drilling, boring. So in your lathe, you got turning, which is outside, parting and grooving, threading, and boring. That's your biggies, and drilling. And of course, some have mills, but most of the mills on your insert types are going to be your face or shell mills, and some have indexable end mills. Those are for your super duper stuff. The only people I ever see use a lot of that was actually at a Boeing plant I was at, and a lot of titanium. Use a lot of insert tooling on the milling. Anyway, that's about it for me on the on carbide inserts and the basics on CNC lathe stuff. Okay, I'll talk to you all later. Bye.